We have 3:45, and it's time to start the second talk in our series. Our first speaker is Piotr Indyk from MIT, and just go ahead.
All right, thank you. First things first, can you hear me well? All right, excellent. All right, so thank you for coming, and thanks to organizer for inviting me. It's a great pleasure. So this talk will be about approximate nearest neighbor search in high-dimensional spaces and its connections to various areas of mathematics, such as geometric functional analysis. All right, so let me start by defining the exact version of the problem that I will focus on. The nearest neighbor search. The input consists of a set of endpoints in some d-dimensional space equipped with some norm. For simplicity, you can think about the norm being Euclidean, but I will consider more general norms as well. So this is the input. Now the output is a little different than described, for example, in the previous talk. Right, in the previous talk, we had some input and what we produce some output. Here, the goal is to build some sort of indexing mechanism called a data structure, which will later help us solve queries of this form efficiently. Right, so what are the queries we want to solve? We're given any query point from this d-dimensional space. We want to be able to quickly identify the closest point in P to Q. Right, so of course we can solve this problem by computing distances from Q to all of the other points, but this takes time, which is linear in the number of points, and if the number of points is large, this is inefficient. Right, so our goal is to add some extra information to the whole process in order to speed up this query time. Now, what is a data structure? I will not define it formally. I will give an example in a moment, but on a high level, a data structure is simply an array of numbers. Right, you can think about the numbers being real or integers, actually doesn't matter really that much, together with an associated algorithm, such that this algorithm, given query point Q, quickly finds the nearest neighbor using the information which is stored here. Right, so this information can, of course, store the coordinates of the original points, but the hope is that as we add more information to this data structure, we'll be able to find the nearest neighbor much faster. So I'll give an example in a moment. Now, if you would like to learn more about data structure, I recommend a paper by Charlie Pfefferman and Boaz Klartak. And in this paper, in the introduction, they give a very nice overview of what data structure is, tailored for a mathematical audience. Okay? All right, but before I start to talk about specific data structures, let me mention two things. Our goal here is dual. So on the one hand, we want to be able to quickly find the nearest neighbor, right, without computing distances to all the points. But at the same time, we don't want to spend too much space to do it, right? And as you will see, there is typically a trade-off between the running time and the amount of memory needed to build this data structure. All right, so a few words about the background. Nearest neighbor search has been considered in computer science literature for a while under different names. So the Minsky-Papert book on perceptrons called it best match problem. Knut in the art of programming called it post office problem. And part of the reasons is that this problem has really a broad set of applications in computer science and other areas. And I will not get into that much detail about the applications. I mean, if you look at the wiki page on nearest neighbor search, there's actually a very nice summary of applications. But roughly speaking, anytime you are searching for similar objects, right, like audio files or images or videos, you need to solve a variant of the nearest neighbor search problem, right? And this is because typically people look for similar objects by lifting them to some feature space, right, high-dimensional feature space, and then searching for similar feature vectors, right? So there are many applications of nearest neighbor. Now, one thing I want to note is that in most of these applications, n is pretty large. Like 10 to the 6 is actually considered a small data set, right? Like 10 to the 9 is more challenging, right? So one has to be really careful about dependence on n, and also the dimension can be pretty large, right? I mean, it can range from tens to millions, right? So you also have to be very careful about dependencies of this algorithm on the dimension. All right, so let's see. Oh yes, and I already mentioned that so there has been many algorithms developed, and many of them are obtained by established connections to well-known theorems in geometric functional analysis or discrete metric spaces, and so on. All right, so let's see a very simple example. This is nearest neighbor search for d equal to 1, and I apologize for anybody who took a basic algorithms class. But I will try to, this is just to illustrate what the data structure is. Right, so in one dimension, the points are just numbers, they are real numbers. And the query point is also a real number, right? So this is the query point. The goal is to find the point in the data which is closest to Q, right? So it's either the left endpoint or the right endpoint of the interval that the query belongs to. And you can see that this is, it just suffices to find one of the endpoints, right? So if you find the right endpoint, we also get the left endpoint, and one of these two endpoints is the solution. So how can we find this endpoint? Well, one approach, again, is to compute distances to all the other points, but in one dimension, we can do much better. Then we can perform a binary search, right? If we sort this array, then we can take our query point, compare it to the middle, and go left or right, dividing the input, and the logarithmic time will find the interval. Right, so this is a very efficient solution. It has a logarithmic query time. Space is also linear. Essentially, we just need to store original points sorted. Right, so in 1D, the problem is very easy. So let's move on to the next dimension, and the dimension equal to 2. Now, in 2 dimensions, we can no longer partition the space into intervals, right? But there is a structure which plays a very similar role, and this is the so-called Voronoi diagram. Right, so this is an example of a Voronoi diagram for the set of points. Right? Those are points. And its Voronoi diagram is a tessellation of the space into cells, such that if you look at each cell, all points in the cell have a unique nearest neighbor. Right? So the nice feature of this partitioning is that it has a low complexity. Right? So if you count the total number of vertices and edges of the cells, if you take the sum, the total is still order of n. Right? So you can compute it and you don't blow up the complexity too much. Then once you compute the Voronoi diagram, then nearest neighbor problem reduces to so-called the point location, where given the query point, you just need to identify the cell that this point belongs to, right? Exactly like in one dimension. Now, this problem is more challenging than on the line, right? Intervals are easy. This is more complicated structure, but perhaps surprisingly, it can be done within the same time bounds, right? So you can also do it in logarithmic query time using a linear amount of space, right? Now here you need to store a bit more information. You build a decision tree, but still you can solve it within the same bounds as for 1D that we have seen before. All right, so this was the good news. Unfortunately, as the dimension goes up, things go downhill from there. And this is because the Voronoi diagram has an exponential dependence on the dimension, right? And this is a ceiling, which means that already for d equal to 3, this is n square, and then very quickly it becomes n cube, and so on, right? And remember that n could be millions or billions, right? So even n square in those situations would be too much. And because of that, all the algorithms for this problem, which have a very small query time, suffer from exponential dependence on the dimension. Now, of course, this is not the only thing we can do. We can also perform a linear scan. As I mentioned earlier, compute the distances to from the query to all the points, but this takes us this much time. And again, if n is billion, this is lots of time. In low dimension, we can speed up this time a little bit, but the speed up diminishes as d grows. And unfortunately, this is pretty much the only solutions that we know for the exact version of the problem. Right, we don't know how to prove that better solutions are not possible, but there is an evidence that indeed improvement might be difficult. In particular, one can show that if there was an algorithm whose query time was sublinear in n, right, and it would be of the form n to some power smaller than 1, and the data structure would take only polynomial time to build, then this would violate a certain complexity theoretic conjecture called the strong exponential time hypothesis. Now, I will not define what it means, because in the very next talk, Virginia Wasilewska-Williams will talk about SET in much more detail. All right, so what can we do if the exact problem seems hard? Well, a natural approach is to relax it, right? Introduce some approximation and hope that the approximation reduces the complexity. And this is exactly what we do. Right, so in the approximate nearest neighbor, we also introduce approximation factor C. And now the goal is, given the query point Q, find a point whose distance to the query is at most C times the optimal. Right, so if the optimal is with distance r, we can report this point, but we can also report this point, right, because it's an approximate nearest neighbor. And as we see, this relaxation helps us greatly reduce the complexity of the problem. Now, in this talk, I will focus on the simpler problem, which lies at the heart of approximate nearest neighbor, which is called the approximate near neighbor, right? So this is the difference. And essentially, it's a nearest neighbor, but for a single scale. Right, so here, on top of the approximation factor, which also given the scale, the radius. And what we want from the data structure is that if there is a point within distance r, we want to report some possibly different point within distance at most C times r. Right, so this is a simpler problem. If we can solve approximate nearest neighbor, we can also solve this one. But in fact, there is a reduction the other way, which incurs logarithmic factors in blow-up, in space, and query time. Right, so up to this factor, these two problems are equivalent, so we'll focus on this simpler problem. And the last thing that I need to define is a randomized data structure, right? So all of this data structure, almost all the data structures that I'll be talking about are randomized, meaning that the algorithm, when constructing data structure, tosses random coins, right? So there's a randomization involved. And what we want then from this data structure is that for any fixed query Q, the probability that the data structure behaves correctly on Q is at least 1 minus delta, where delta is a parameter. Okay? All right. So this is the definition of the problem that we'll focus on. All right. So a little bit of a background on approximate nearest neighbor. So this problem has been studied quite extensively over the last couple of decades. And there were essentially two waves of algorithms. The first wave started in the early 90s and led to development of algorithms whose either space or time were still somewhat exponential in D, but they were much milder than n to the D. Right? So for example, D to the D was a typical bound. And then the second wave started in the late 90s and led to algorithms with both space and query time were polynomial in the dimension. Right, so in this talk, I'll focus on the second class. All right, so what's the plan for the rest of the talk? I'll try to give you an overview of the state of the art in the space. So what are the bounds and techniques for the data structures? I will split it into two classes. Right? So in the first class, I will describe so-called non-adaptive data structures. So in a way, these are data structures which almost are like cookie cutter data structures. Right? They use very limited information about the data when they actually construct this data structure. And they have certain limitations, but nevertheless, they work for L1, L2. And I will describe two basic techniques for developing that can be used there. In the second part of the talk, I will focus on a more recent adaptive approach, right, where the data structure actually uses more information about the data. And we'll see that adaptivity can help develop both faster algorithms and more general algorithms, right? Not only for L1, L2 and relatives, but in fact for general norms as well. All right, so let's start from the non-adaptive data structures. Now, I should define what non-adaptive means, but I will postpone it until 2 slides from now. Okay. Instead, I will start from describing perhaps the simplest approach to high-dimensional approximate nearest neighbor search, which goes through dimensionality reduction. Okay, so what is the idea here? Well, for simplicity, let's consider approximation factor to be at most 2, and just for notational purposes, and let's set epsilon to be c minus 1. So the dimensional reduction approach proceeds in 2 steps. In the first step, design a data structure which has very efficient query time and whose space is only of this form, right? So it's a constant to the power of d for a constant epsilon. And the second part, we take this space with a high dimension and just reduce the dimension by applying the well-known Johnson-Lindau-Strauss lemma, which, so this theorem holds for L2, and it tells us that we can reduce dimension to log n over epsilon square while preserving all the distances up to 1 plus epsilon. Okay, so now if you take such a data structure and if you apply dimensional reduction, you get a data structure with roughly this space and this time. Now, technically, if you combine these 2 things, you get something slightly weaker than this. But if you add some extra work, you can obtain this bound as well. All right. So if you look at this result, there are 2 good news and 1 bad news. So the good news is that the query time is very good. And the second piece of good news is that for any fixed epsilon, this is a polynomial space. Right? Now the bad news is that there is a constant here, right? Hidden constant here, and this constant is not large, but it's definitely not negligible, and it lives in the exponent. Right, so there is, this constant is a product of this constant and this constant. This constant are not large, but once you multiply them, even for epsilon equal to 1, you are just not getting a practical data structure, right? Because remember, typically even n square or n cube is just, too much to handle. Right, so this algorithm, this is a theoretical result. It shows that you can avoid exponential dependence on dimension, but in practice, the space is too large to be practical. So because of that, people, through the research, focus on getting space down, right, to something more manageable at the price of increasing this time. Okay? And the technique which became very useful in this context is random space partitions, also called Locality-Sensitive Hashing or LSH. So there are several definitions of LSH. One of them is the name of the hotel in Baja de Tijuca, not far from here. I recommend this hotel, it's excellent. But this is not the definition I will focus on. The definition, I will focus on the second definition, which is specified here. So, consider a family of functions of this form, right? These are just a mapping from a d-dimensional space into some finite universe U, right? So this is essentially a space partitioning, right? Where each cell is labeled by an element from U. So we say that this family is sensitive with these parameters, P1, P2, R, and CR. Right? R is the radius, C is the approximation, P1 and P2 are probabilities, if the following 2 things hold. So if you have a pair of points which are within distance R from each other, so we can call them close, then if we choose a hash function from this family at random, then the probability that P and Q belong to the same cell is at least P1. On the other hand, if you take a pair of points which is within distance at least CR, so we can think about them as far points, then the probability of collision is at most P2. Right? And the idea is that I would like to have P1 greater than P2, so that the probability of collision depends on the distance, right, between the 2 points. Now, suppose that somebody is nice enough to give you such a family, then you can automatically use it. Okay, there is okay, I'm just going to move up. So then there is there is an automatic way of converting this family into a data structure, which uses this amount of space and this amount of time. Basically, both of them are linear in L. Well, L is of this form. It's essentially n to the rho, where rho is the ratio of the logarithms of these 2 probabilities. Okay? So what's happening here? Well, think about P1 and P2 as constants, right? So then this disappears. And if P1 is greater than P2, then log of P1 is smaller than log of P2. right? Which means that rho is smaller than 1, which means that you get a data structure whose query time is sublinear in n, right? It's n to some small something which is less than 1. And the space is also never larger than quadratic. More typically, it's actually can be pretty close to linear. All right, so how to show this reduction? It's actually not, I will not give a proof, it's not very complicated. The basic idea is to take those family of hash functions and use those, take one at random and map it into beans, right, where each point is mapped to a bean, point P is mapped to the bean H of P. Okay, and then we do exactly the same for the query, right? We take the query point and map it to some bean, and then we simply look at all the points which were mapped to this bean, enumerate them, and find the, base the answer on the points which are stored in this bean. Now, we cannot quite do that because, in principle, P1 and P2 could be constants, right? So if P2 is constant, it could be a constant fraction of far points which are, of points which are mapped to a single bean, so just enumerating them would take too much time. So instead, we just amplify this gap by concatenating several hash functions, and this pushes down both P1 and P2. And because P1 is pushed down, we have to repeat this whole process several times to ensure that the close point to Q is put in the same bean as Q with at least some probability. Right, and the number of repetitions exactly this parameter L, right, which is why both the space and time are linear in L. All right, so basically this means that it suffices to come up with such families. So let's see some examples. Oh yes, and finally I can say what does it mean that a data structure is non-adaptive. Basically, non-adaptive means that memory cells' access to answer queries depend only on Q. Okay, not on the data set. So this is true here because if you want to find the near neighbor of Q, then you only look at cells where Q is mapped, right? You don't look at any other cells. So you are, in a way, completely ignoring the set P in this process, right? The only place where P comes is when you look at the points contained in the cell, right? So this is basically means that the algorithm is like very much cookie cutter type of thing, right? The data structure is not tuned too much to the data. All right, so let's see what are the examples of LSH functions. A particularly simple example holds for L1 when all the coordinates are binary, because in this case, you can just take a family of all projections on one of the coordinates. Right, so there are D coordinates, there are D projections, which means that selecting a hash function at random and applying it to P just corresponds to sampling one bit at random. Right, so if you do it, then it's easy to see that probability of collision is equal to the fraction of positions on which P and Q agree, which is 1 minus fraction on which they differ. Right, so you get this formula, and it depends linearly, probability depends linearly on the distance, which means it's a sensitive family, right, because it depends on the distance. And after you perform some calculations, you get exponent equal to 1 over C, where C is the approximation factor. So it's helpful to illustrate this running times for a particular value of approximation. As you can set C equal to 2. And in this case, you get an algorithm with an exponent 0.5. Right? So you get a running time of square root of n. In fact, this approach works for general RD under any LP where P is between 1 and 2. So this was one of the first examples. But after that, development in '98, there has been took some time to develop something better, and in big part is because we're trying to get better hash functions for L1, while it turns out that more progress is possible for L2. Right, and in particular in 2004, we proposed the following hash function, which is tailored to L2. We take a point and perform random dimensional reduction into one dimension. And then basically means that we project the points on a random line, and then we split this line into intervals, and the ID of the interval is the hash function that we output. Right, so intuitively it is sensitive. After you perform calculations, you can show that it has exponent rho, which is slightly better than 1 over c. In particular, for c equal to 2, you get 0.45. Right? So this is not a big improvement. Right? It doesn't affect the empirical runtime. But nevertheless, it shows that something interesting is happening for L2, which was not happening for L1. And a couple of years later, we managed to generalize it to improve over the bound, and the generalization is actually quite natural. Instead of projecting on a line, project on a constant dimensional space, and then we have to round. But it turns out that rounding using intervals or product of intervals doesn't give any improvement. Instead, what you need to do is to round using a lattice of balls. Right? So you impose the lattice of regular space balls, and then if the point actually falls into one of the balls, you return the ID of this ball. Now, of course, in high dimensions, even in the best packing, there is lots of empty space, right? So chances are that the point is not going to fall into any ball, so you just repeat this process until, with different randomness, until you hit at least, until you hit one ball in, one of the chances, right? So this leads to space partitionings that look like this, right? You just keep carving balls until the whole space is covered. And you can show that this approach indeed improves over one dimension, and in particular, rho tends to 1 over c squared as the dimension tends to infinity, right? And the convergence is actually pretty quick, which leads to an algorithm with a query time of the form 1 over c squared, right? So for c equal to 2, you get a fourth root of n in terms of runtime. Here you just, I put the year, right? But this is not that important. All right, so that was the state of the art in 2006. But well, actually, this is where the progress stopped, for almost a decade. But this time it stopped for a good reason. Namely, a sequence of follow-up papers shows that, in fact, any LSH for L2 must have rho at least 1 over c squared, unless probability of collision is so small that the data structure is not usable. Right, so essentially this means that improving the algorithm by designing better space partitionings, is just not going to work. Right, so one has to develop some other methods if you can hope for getting a better running time. And this brings us to adaptive data structures. Right? So this is a pretty recent work which shows that by being a little bit more careful in designing those data structures algorithmically, you can improve over non-adaptive data structures. All right. So what's the idea behind those algorithms? Well, the idea is essentially to design data structures which depend on the data, right? So, if you think about it, this is like pretty obvious idea, right? I mean, there is absolutely nothing deep about this. So why it took so long, almost a decade, to get some improvement? Well, the reason is that it's often possible to get a data structure that works if your data has some particular structure, right? So you can tailor your data structures, for example, to the case where points lie in a low-dimensional space, or have some clusterability, or rely on a low-dimensional manifold, and so on. But in our case, we want a data structure which works in the worst case, right? For arbitrary set of points, okay? And this means that you also have to get some improvement where the data does not, what's cut here, does not have any structure. Right? You basically cannot just rely on taking care of some structure, you also have to take care of the complement. And because of that, this is a little bit tricky. So what's the solution to that? The solution turns out to be quite easy, or natural, at least on the high level, which is to show that every point set has some structure that can be exploited algorithmically. Right, and the details of this depends on the particular algorithm or a problem, but at the high level, it relies on the following dichotomy. if you look at your set of points, either you have a dense cluster of small diameter, okay, or not, right? And in both cases, you can often design better algorithms, right? So if there is a dense cluster, then you can design something for a dense cluster, knowing that it takes care of a large fraction of points in your data and it has small radius. And if your points doesn't have dense clusters, then it means that points are spread out, right? You can say points that is hollow. And in this case, you can also benefit algorithmically. And as we see, this leads to both faster algorithms and more general algorithms, right? So let's see how you can get faster algorithms using this approach. All right, so here is the simplest example of what can you do. Well, you take your data set and you start from preprocessing. Right, you just go over your data set, and as long as there is a ball of radius order of CR, right, C is the approximation, R is the radius, which contains at least some number of points, I will not define it here, then you remove it, okay, and you look for the next cluster and so on, and you finish when there is no dense cluster in your point set. And then you build a nearest neighbor, for example, locality-sensitive structure for the hollow point set, and you also build it for each of the points of the clusters that you removed. Okay? And during the query time, you do the natural thing, which is you query both, right? So you query the main data structure for the hollow set, and you also query all data structures corresponding to clusters, which are close enough to query so that they can contain an answer. All right, so why, on a very high level, why it leads to some improvement? Well, in the first case, you can use the no dense cluster property to basically no dense cluster property means that most of the points in your data set are actually very far from the query, right? Like much further than CR, because if there will be many of them within distance CR, you'll have a cluster, right? And you don't. Now, if most points are far, right, then for those points, probability of collision with your query is actually much smaller than before, right? It's you can actually show that it's small, and you can utilize this reduction in probability of collision of far points to get to use fewer hash tables. Okay, so in this case, you win because of that. Now, if you know, on the other hand, that the diameter of your points is bounded by order of CR, then it turns out you can design better LSH hash functions, right? So the lower bound that I mentioned doesn't apply for the case where all points have bounded diameter. And in fact, you can design better hash functions which are parameterized by the position of this ball, right? So you can see that this algorithm is very much adaptive. Right? I mean, definitely does something not trivial with the data. It exploits the structure. And, it turns out that in both cases, you can get some improvement, and this leads to overall improvement in the query time and space. Okay? So specifically, a generalization of approach that I described improves the exponent by a little bit, right? By a factor of 0.87. Assuming that the approximation factor is large enough, right? So the improvement kicks in only for larger values of C. So this shows that there is some benefit coming from adaptivity, but the full power of adaptivity was only utilized by these people, and basically they managed to reduce the exponent almost by a factor of 2, right? So again, looking at our example of C equal to 2, right, the improvement, the exponent goes down to 0.15. Okay? And this is where this exponent is right now. It's not clear how to improve it even further. My best guess is that I need to come again with another set of ideas to get this improvement going. But you can see that there has been a considerable improvement in the complexity of the problem over the last couple of decades. All right. So in the last part of my talk, I will focus on another application of adaptivity to get algorithms that are more general. So far, using non-adaptive methods, we managed to we have seen two techniques for non-adaptive methods. One of them was dimensional reduction. Johnson-Lederschaf's theorem, as is, works in L2. And unfortunately, this approach doesn't really generalize that much because already for L1, there are lower bounds for dimensional reduction in a very strong sense. And furthermore, Johnson and Nauer proved that any space which supports dimensional reduction with a small distortion, in fact, it's essentially L2. I mean, it's not exactly L2, but it's up to so-called a log star factor away from L2, right? So this means that straightforward dimensional reduction is limited to only Hilbert spaces or very close to them. Locality-sensitive hashing is a little bit more general. It works not only for LPs, for P between 1 and 2, but also other similarity measures are actually very useful in practice, but it doesn't work, for example, for L infinity, right? You just cannot get anything non-trivial using it. And there are other ways to extend those results. One is actually pretty immediate, right? If you can solve near neighbor for some norm, you can also solve it for small powers of that norm, right? Because near neighbor operates in a fixed scale. Now, this affects the approximation factor, but not generality, right? So this is very useful because we can solve it, for example, in so-called L2 square. And last but not least, you can take other spaces like edit distance, transportation norm, and embed them with low distortion into, say, L1. Right? So combining embeddings and algorithms leads to algorithms for those spaces. So this increases the applicability of those methods, but in a way, the techniques are very pointwise, right? Because if you want an algorithm for some space, you take this particular space and embed it into L1, right? Or you develop a different hash function for L1 and L2, right? So there is, until very recently, there has been a very limited general theory, right? Like one algorithm that works, for example, for all norms. And that changed quite recently, but before I describe that, let me just make a very simple observation, which is it is easy to get an algorithm for any norm, but with a very large approximation factor, right? And this is because you can take any norm and embed it into Hilbert space with a square root of the distortion. So this works, but the square root of the is pretty large. The first generalization of the methods that I described earlier was developed in a recent work by Andoni et al., who showed that any symmetric norm can be embedded in this very strange-looking space, right? It's essentially L infinity of L1 of L infinities, right? So this is like a product space. And surprisingly enough, for this space, one can design approximate near-neighbor search algorithms. And by combining those algorithms with the reduction, it yields approximation factor, which is a polynomial in log n. Right? So it's not constant, right? But for reasonable values of n, this is much smaller than this. And that was a state of the art in 2007. But in 2018, almost the same set of authors presented an algorithm which works for any norm. Okay? And the main notion used there is a cutting modulus, which I will discuss in a moment. And this leads to algorithms with the approximation factor of log d. Right, so again, it's not a constant, but it's exponentially better than what we knew before. I'm not listing here space or time, but they are very similar to locality-sensitive hashing. Right? It's just the approximation factor is slightly different. Now, there is one important caveat, which is that this algorithm is more of a proof of existence, right? Because this algorithm operates in the so-called cell probe model, which means that we are accounting only accesses to the data structures, right? We don't account for the time it takes to process what we get from these data structures, right? So this is more of a proof of existence than an actual algorithm, but the good news is that it can be converted into an actual algorithm. If you focus on specific norms like LPs. Alternatively, you can get an algorithm, actual algorithm for any norm with a somewhat worse approximation factor. Right? So instead of log d, you have something like 2 to the square root of log d, or something like that. Right? Which is still much better than what was previously known. And the 2 to the square root of log d is a result which is yet unpublished. This paper here is very recent, was just presented at the Stock conference a few weeks ago. All right, so in the remaining few minutes, let me just give a very brief outline of these techniques here. So the key notion is a notion of cutting modulus. Unfortunately, I don't have time to define it. Okay, I apologize for that. Let me just mention this parameter, which can be defined for any metric space, and error parameter alpha. And the key result here is that Asaf Naor proved in 2017 that cutting modulus is at most log of d or for any norm space over RT. Okay. So this is the only thing I will say about the cutting modulus. Now, this is an outgrowth of Asaf's research on nonlinear spectral gaps, and if you want to learn more about these notions, Asaf will give a talk about it next week. Right? So I don't know if he will define cutting modulus, but he'll definitely talk about nonlinear spectral gaps. All right, so suppose that we know that there is this parameter, which is at most log d. So what can we do? Well, at the heart of the algorithm is a partitioning procedure, which is encapsulated by this theorem. So what does this theorem say? So consider our metric space. Let's assume it's finite. We can always discretize it. And let's take 2 parameter alpha and the radius r. Right? This is the r from the nearest neighbor. Then they show that there is a small, I will not define small, a collection of subsets of the symmetric space such that for any data set of points P of size n, we have the following dichotomy. Right? Either this point set contains a dense cluster, right, of small radius, namely of radius, which is the cutting modulus times r, and dense means that it has at least linear fraction of points. Right? So this is one situation. If this is not the case, then alternatively, there is a distribution over sets from this partitioning, which are partitioned the set of points evenly, approximately, right? So both sides of the partition are linear in n. And furthermore, for any 2 points in the metric space which are close, we have the property which looks very similar to locality-sensitive hashing. Right? Probability that this partitioning separates x1 and x2 is at most alpha, right? Where alpha is our error parameter. So suppose that we believe that this theorem is true, then it almost immediately leads to an algorithm, because in this case, when there is a dense ball, then things are good, right? Because lots of points lie in a cluster of radius order of r, and since we don't care about the constants here for approximation, it means that we can collapse all of them into a single point. Right? So we just reduce the whole data set by a constant factor, and we can just proceed recursively. On the other hand, if we know that there is such a randomized partitioning, then we can use a LSH-like algorithm, again, to solve this problem reasonably efficiently. Right? So this theorem is at the heart of the data structure. And it leads to an algorithm whose approximation factor is proportional to the cutting modulus, right? Which, as in the previous slide, is always at most log d for any d-dimensional norm space. Right, and the reason why this is an algorithm which operates in the cell-prop model is, has to do with, what these collections are. Can we compute them efficiently, and so on, right? So this is the part that, is not always constructive. All right, so that's the end of my talk. So just to conclude, so what I describe are approximate nearest neighbor search data structures. I described the work done over the last couple of decades, and we have seen this slightly older non-adaptive methods, which works for L1, L2, and relatives, but they have some limitations. And we have also seen more recent adaptive approach, which led to faster algorithms and more general algorithms. And also outline strong connections to geometric and metric functional analysis, right? We use Johnson-Lindershoff theorems and many other things, right, which are very useful to design algorithms here. Now, many things are solved, but there are still many interesting open problems, so this is just a sample. All the algorithms I described are randomized, right? Converting them to deterministic ones will be very interesting, right? Very little is known. You can see the proceedings for more details, but there's more algorithms, more results known for so-called Las Vegas version, where the algorithms are still randomized, but they don't make any errors, right? But occasionally they can just say, I don't know. Right, so if we allow this extra option, then analogs of these algorithms are known, but they are not deterministic, right? So it's an interesting question. And I didn't talk, I focused on the norm spaces in this talk, but this problem is very interesting for metric spaces like eddy distance. And some results are known by embedding into L1, but in particular, this is still an open problem, right? So you can get approximation, which is roughly 2 to the square root of log d, but getting something even polynomial log d, it's a major open problems. We don't know it. And the same question holds for transportation norm, except that in this case, log d is known. It's a norm. But getting something which is significantly better is still an open problem. And that's it. Oh yeah, and last but not least, if you are users of nearest neighbor, we have a software, like if you Google Falcon with 2 N's, right, it's going to get you to the GitHub, which contains the software which you can use. And now it's really it. Thank you.
Thank you very much. Questions, please.
What about... Please use the What about projecting onto several random lines and looking for common neighbors?
Right. In a way, this is what we do because, if you remember, oh boy, I guess getting back might take a while. If you remember, the actual algorithm at the end doesn't use just one single hash function, but it uses multiple hash functions, right? So, for example, here, each hash function corresponds to projecting on several lines, right? So in a way, we are already doing it here, right? Yeah. But it's possible that there are some techniques, algorithmic techniques that we didn't think of, right? We don't have lower bounds. Yes.
More questions.
Is there any advantage one can get to be adaptive to queries? So change your data structure as the queries come? Adaptive in
queries?
Adaptive time.
Yes.
Adapting to the queries as they come.
Yes. So in a way, yes, in the sense that if you focus on a batch version of the problem, so all the queries are given to you in advance, right? So this is like a very strong assumption. But then you can actually get better algorithms than if you process those queries one by one. Right, so then, this is so-called all pairs nearest neighbor problem, and there is lots of exciting developments by Greg Valiant and Ryan Williams and so on, which improve over what is known here when epsilon is close to 0. Right, so that's now. If we don't know all the queries in advance, then I don't know if there is any hope. Yeah, to the best of my knowledge, this is still the best thing that is known. That's an interesting question, though.
I see no other arm, but I have 2 questions. I'm
Sure.
a very practical person, and The question, you have concentrated on runtime and space analysis.
Correct.
So algorithms often run differently in real application, implementation. Are these algorithms much faster in practice than in theory? This is one issue.
Sure.
In the second issue, you mentioned you have data sets with 10 to the 9 data points and 10 to the 6 dimension. How fast actually is a query there? How fast do you answer?
I see, sure. So I have some plots. So there is a very nice, how do you call it, setup called the NN benchmark. So this is by third party. I think these are the authors. And this is like a common test bed for many of these approximate nearest neighbor search algorithms. So they basically, once you put your algorithm in GitHub, they can run it and plot the curve. So this is coming from the paper by these folks here. So what you see, I think that this is on Glove data set, which I think has at least a few million points. I don't remember dimension. I think it's 64. And so what you see here are the plots which plot the throughput. Throughput is 1 over query time, right? So the higher, the better. And as a function of the recall that you get, right? So if you want the, basically you search for the here for the 10 points, and this is the fraction of the true top 10 points that you get, right? So ideally you would like to be up and to the right. And what you see here is, let's see, Falcon. Yeah, so Falcon is here, right? So, for recall, which is not perfect, but, like up to, 0.7 or so, the algorithm is actually pretty efficient. And 1 over this gives you the actual query time. Okay. Yeah. So now, to be fair, this analysis was done, I believe, on a single core. Once you get implementation details, this curve changes.
There's a website where you can look that up.
That's correct. Okay, that's correct. If you look at the ANN benchmarks, you can find it there.
Thank you.
Yeah.
I see no more hand, and I'd like to thank you very much again.
Thank you.